In the case of a flat highway, the only force that can cause you to turn in a circle is friction. But friction is unreliable. When the roads get wet or icy, there is no friction or very little friction to help us turn that corner. And so we overcome that problem by banking the road. Now, I have a hard time drawing banked angles in 3 dimensions, but essentially instead of taking your road flat, you increase the angle and it slopes in towards the center. So I have just a cross section of this here, and so your car sits on this and it's driving, you can think of it as towards the camera, towards you, and then it's going to curve in to the right. And so when you do this, there's actually another force that can help you turn that corner. And let's take a look at why. If this was sitting at rest here, there would only be 3 forces acting on it. There would be gravity pulling straight down, there would be the normal force perpendicular to it, and then there would be friction preventing it from sliding down the incline. But we're not going to put it at rest, and we're going to ignore friction. So this thing is driving straight towards you, and this is curving around like this, which means the road is actually curving in front of you, and it's going to push you around all by itself, right? We don't need friction to do that. And so what happens is now there is gravity pulling straight down, just like before, and there's a normal force going this way, but because you're driving into the road is pushing back on you, and so the normal force is actually greater than if you were just sitting at rest, because a component of that normal force is going to help you turn that corner. So I'm going to look at the frictionless case. And so this is the normal force. We are moving into the in towards the camera around this corner at some speed v, and so there is a force this direction, Fny, that will actually balance gravity, because this thing is not accelerating down the incline. In fact, it's not shifting its position on the incline at all. The center of this corner is somewhere over here, and it's only centripetally accelerating, which means the acceleration is still in this direction, which means my positive x and y, I'm not going to rotate those along the incline, because it's not accelerating along the incline, it's accelerating towards the center. We want our frame of reference to show us the acceleration in only one dimension. X dimension is towards the center. So Fn is this way, Fny is this way, and Fnx is this way, and the force, the only force that's pushing in towards the center, is the normal force in the x direction. And so that's what's supplying our centripetal force. Now this bank angle here is the same as that angle there. And so what I can say is the net force in the y direction, which is Fny minus Fg, that is 0. So the normal force in y will balance gravity in y. Those two things add up. So I can say Fny equals mg. Okay? The net force in x is just Fnx, which equals mv squared over r. It's causing it to accelerate centripetally. Now, I want to find the design speed for a certain radius, that is the speed at which no friction is required, so just like I have here, in order to turn this corner. And to do that, I'm going to start making some substitutions. So Fny, how is that related to Fn? Well, Fn times the cosine of theta equals Fny. So Fny equals Fn cosine theta. So I can make that substitution here, and I will in a second. And Fnx, that's opposite that, so that's going to be sine Fn sine theta. So I can do that. All right. So I have Fny is equal to mg, but instead of Fny, I'm going to use Fn cosine theta. So Fn cosine theta equals mg, which means Fn is equal to mg divided by the cosine of the bank angle. Now right here, I have Fnx equals mv squared over r, but Fnx is really Fn sine theta. So I'm going to go ahead and replace that. Fn sine theta equals mv squared over r. But Fn is really mg divided by cosine theta. So I have mg over cosine theta times sine theta equals mv squared over r. And that means that mg tangent theta equals mv squared over r. I can divide both sides by m, multiply both sides by r, and get g times r times the tangent of the angle is equal to v squared. And so the design speed for this road is given by this equation. I guess I'm going to square root both sides and get v equals the square root of gr tangent theta. So that is the bank angle. That's the radius. It's the acceleration due to gravity. The square root of their product gets me the design speed, or the speed at which no friction is required to turn this corner.